So we've been talking about resistors, and what is a resistor? Well, the light bulb in the circuits that we played with, that was a version of a resistor. All right. Resistors are pretty much any device or material that conducts electricity, but inhibits current flow to some degree. And they consume electrical potential energy and convert it into heat, typically. Now, in the case of a light bulb is a resistor made of a material called tungsten. It's very tiny. It's inside the bulb, that little spring in there. And that tungsten gets hot because of its resistance to current flow, just like friction in regular Newtonian mechanics. And it gets hot, and eventually it gets to a certain temperature and it starts to give off light. Radiation. All right, well, resistors can look like other things too. Here are a couple resistors, kind of two extremes. The one on the left is made of a metallic film that can be modified to have different resistive or conductivity, you could say. This is a large resistor, probably made out of carbon material. This large one can dissipate much more power than this little one. This little one might be maybe a half a watt or 250 milliwatts, something like that. This one here can dissipate, let's see, I saw it on here earlier, 50 watts, meaning it can handle a lot of current before it burns up. Put too much current through a small resistor and you can burn it up. It gets too hot and it literally burns and it's broken. Now, resistors are used in circuits. So here are a couple of circuit boards. They're using circuits to control current flow, right? A couple things to note here. Here's an integrated circuit inside of this black packaging. It has many different connections that you could find a drawing of online and use in a circuit. And inside of this is a piece of silicon that probably has thousands of little tiny microscopic resistors on it. The board itself has some resistors on it. Probably these two items right there, three of them there, are probably resistors. Note that they're close to where you plug in the USB cable. Resistors are often used to control current flow, so might be some power management going on over here. This is called an Arduino. It's basically a little computer that runs one program at a time. It can only have one program loaded on it that it will just keep running nonstop as soon as it's turned on. This little device is a kind of a cool thing. You can put a bunch of batteries into this and it outputs a steady 5 volts USB, right? 5 USB are 5.1 volt power connectors. Now there's 4 connectors. One will be positive, negative, and then 2 will be for data, on the USB connection. And the 2 that are for data, you can really send lots of information down. So we use USB cords for a lot of things, charging, but also to hook things up to computers to send information back and forth between a device and a computer. So this thing has a bunch of resistors on it here, another one over here, and it's all used to control the current flow for some reasons, for some degree. So this can take any voltage between like 3 and 12 volts and output it. You plug them in here. So you plug batteries into here, any 3 to 12 volts, and it outputs 5 volts, a nice steady 5 volts for, use for your phone or whatever, charging your phone, charging something, whatever like this. So anything that conducts can be a resistor, right? And it turns out different materials have different resistances, or I should say resistivities. The symbol rho represents resistivity, and the units are ohms times meters, not ohms per meter, ohm meters these are. Now this number, what does it mean conceptually? Basically, the bigger this number it is, the harder it is for that material to conduct electricity. So What's cool is all of these have the same scientific notation order of magnitude to the -8th. So really all you have to do is compare the prefixes here. So the best conductor, meaning the lowest resistivity, is silver on this table. I don't know if any of the other metals are a better conductor, but they're certainly more expensive. The worst conductor on this table would be nichrome. Nichrome's kind of a neat metal, very high resistance. Pretty shiny, doesn't rust too easily, used in a lot of different applications. Kind of a neat material. Tungsten, also used in a lot of applications. High resistance, higher than anything else. But what's cool about tungsten is its melting point is quite high. I forget the exact number. So we use tungsten for light bulb filaments. Tungsten heating elements are often a tungsten-based material or alloy. It has a high melting point, so you can get it hot and get red hot, and it won't disintegrate and catch on fire. It just glows red hot and puts out a lot of heat. When you take one of these materials and have it in a wire or a piece of one of these, it's a resistor. You can put it in a circuit and it'll act like a resistor. Now, not very good resistors, because these materials aren't really that resistive other than nichrome. Like I said, these are materials where the conductivity or the resistivity is manipulated by mixing different materials together. All right, so this is a carbon material that you mix metal in, and the more metal you mix in with the carbon, the more conductive it is. This is a metal film, which is a similar thing. It's like a polymer metal mix, which is kind of an interesting thing. So ultimately, what we're doing with this is basically calculating the resistance of wires. We saw in the real lab that wires did have a voltage drop, right? In the ideal circuits we studied in the last worksheet, we pretended that wires did not have a voltage drop, but in our lab we saw wires dropping anywhere between 0.02 volts all the way up to half of a volt. And it could be for a variety of reasons. Bad alligator clips is the most common culprit. It's usually not the actual metal the wire's made of. It's usually a bad connection that causes a high resistance for a wire. So if I take some of this metal and I make it a certain length and a certain cross-sectional area, that could be a rectangle as well. It doesn't need to be a circle. The equation becomes this. The resistance of a wire or a piece of material, chunk of material, is the object's resistivity multiplied by its length divided by its cross-sectional area. So let's just jump into this and do some math here. Get our fun resistors out of the way. Determine the resistance of a 50 centimeter piece of nichrome wire with a cross-sectional area of 4 times 10 to the -5 meters. All right, so R equals rho L over A. I like to write a rho, that's kind of fun. So I'll plug in the variables. Nichrome, so it's 150 times 10 to the -8 ohm meters. Ohm times meters. The length of the wire is 50 centimeters, but you know you got to put it into meters, so 0.50 meters. Cross-sectional area is 4 times 10 to the -5 meters squared. Now, usually they don't give us meters squared for a wire, right? The conversion rate is crazy. I'll show you that in a second, between millimeters squared and meters squared. It's 1,000,000 millimeters squared in 1 square meter. So I'll talk through that a little bit here in a second. So 150 times 10 to the -8 times 0.5 divided by 4 times 10 to the -5. So 0.019 ohms. So that's really not that big. Resistances of like what we did in class, right? We saw, 1.5 volts, divided by 0.25 amps. We had about 6 ohms, the resistance of the light bulb circuits that we were looking at. So that's a tiny resistance. So wire, even the worst conducting wire, it does not make a very good resistor. You know, even the worst piece of metal is still a pretty good conductor. So that's why we got to make special blends of stuff to get higher resistivities. All right, to make actual resistors. So 12 gauge copper wire used in bathroom wiring. So by bathroom, I mean household, like in the walls of your bathroom, the wire that carries the light between the switch and your fan or your light is 12 gauge copper wire. Now 12 gauge wire has a diameter. So a wire that's 12 gauge, 12 GA, is, I think they say AWG actually, but is 2.0 millimeters in diameter. All right, so that's the diameter is 2.0 millimeters. Now, all right, let's see what the question's asking us before we continue on here. So this is kind of like a cutaway of one of the ends. All right, determine the resistance of a 25 meter, so that's the length, that's diameter, piece of this wire, so copper. We'll have to look up that resistivity, but we'll get there. So R equals rho L over A. Now, I need to find the cross-sectional area. All right, so what I'm going to do is A equals pi R squared. All right, and that's D over 2, so it's 1 millimeter. But I got to put in not 1 millimeter, so it's 1.0 millimeter radius, which is 1.0 times 10 to the negative third meters. You're going to want to put that in right instead of millimeter. The conversion is very kind of a pain if you don't put that in the beginning. So the cross-sectional area, a little bit of a side calculation we have to do first. 3.14 times 1 times 10 to the negative third times 1 times 10 to the negative third. Cross-sectional area is tiny. It's 1, 2, 3, 4, 5, 6. 3.1 times 10 to the negative 6, 1, 4 times 10 to the negative 6 meters squared. So the resistance of that wire in your house, well, we gotta look up the resistivity. Copper, 1.72. 1.72 times 10 to the negative 8th ohms times meters. The length is 25 meters. That's actually, there's probably no wire, piece of wire in your house that's 25 meters long. In the school, there definitely is. In our school, for sure. But 25 meters in your house, that would be quite long. But you never know. Cross-sectional area is 3.14 times 10 to the negative 6th meters squared. Again, the units meters are going to cancel out, so now we put this all in. 1.72 double E negative 8 times 25 divided by 3.14 double E negative 6 is 0.14 ohms. So very low resistance. And the reason we want bathroom wiring to be low resistance is because some of the things we plug in the bathroom, in the bathroom, are high current drawers. They draw a lot of current, like a hair dryer, a curling iron, a hair straightener. You know, the vent itself, that's usually on a separate circuit actually. But we plug in some pretty high current drawing items in the bathroom. So by code, it must be a 20 amp circuit, and you have to use 12 gauge wire. So bigger wire, less resistance. Bigger wire, less resistance, therefore less heat generated, and more current can be delivered. All right, so a resistor of unknown material has a resistance of 200 ohms. Okay, so some unknown resistor. I draw as a little cylinder, right? R equals 200 ohms, okay? What would the resistance of a second resistor probably be a comment there, made of the same material and of the same length be if its cross-sectional area was doubled. So let's say I went from that to this. So it's the same length, right? But A is doubled, right? Okay. So if I double across the equations, R equals rho L over A. Well, R new would be rho L over 2A. So R new is 1/2 of your original resistance. So the new one's resistance would be 100 ohms. So doubling the cross-sectional area halves the resistance. And what's cool is to double the cross-sectional area, you actually don't have to double the radius, right? You only have to do radical 2, 1.4 times the radius to get us double the area, which is nice, you know. So it doesn't cost that much more to use bigger wire. You could use that wire throughout your whole house, really 12 gauge wire, but the problem is it is actually a little bit harder to bend and move through the wall because of its increased thickness, increased diameter. What would the resistance of a second resistor made of the same material and the same cross-sectional area be if its length was quadrupled? So this is the original. I'll draw it like this. So that's 200 ohms. We'll say that's L. And let's say we quadruple that. So 1, 2, 3, 4. So it's like we took the same material, we just made a longer resistor out of it. 4L. What's its resistance? Well, again, R equals rho L over A, and R new is rho times 4L over A. So it's 4 times rho L over A, which is 4 times your original resistance, or 800 ohms. 800 ohms. So it's just like putting resistors in series. You're making it longer, the resistance is going to go up. All right, this last question here, I really like this little question. A 10 centimeter long 2x2 block of material is connected to a 12-volt battery in a simple circuit. The block of metal draws 0.75 milliamps of current. Determine the resistivity of the unknown material. So this is cool. It's like, okay, we got some new material we found. Let's see if we can figure out what it is, right? So we take it and we set it up in a circuit. So let's make a little 12-volt battery. Let's draw it. 12-volt battery. We take this material. It's a uniform thickness and size. I'm going to draw it like this. Oops. All right, it's 2 centimeters by 2 centimeters by 10 centimeters in length. Got a wire hooked up to it. Draw 0.75 milliamps. All right, so let's calculate its resistance and then find its resistivity. So R equals V over I. So it's 12 volts divided by 0.75 milliamps. All right, so let's do that math. 12, oops, I got an imaginary number I in there. 12 divided by 0.75, that gives me, oh, what am I doing? Harmon, you fool. 12 volts divided by 0.75 times 10 to the negative third amps, right? This would tell me how many kilo ohms it is. It's gonna be 16 kilo ohms. Because if I divide volts by milliamps, that gives me kilo ohms, but I want to probably do that the right way. 12 divided by 0.75. Electricians and stuff deal with this stuff all the time on the daily basis. So do engineers, electrical engineers and others. And we really do just, milliamps is a really common unit to divide by, and we know usually we're dealing with volts and milliamps and kilo ohms. We just know from repetition that that's the way it's going to go. So now I can say, okay, R equals rho L over A. All right, cross-sectional area is 0.02 meters by 0.02 meters. My light's turned off, but I think the window's casting enough light. I don't want to waste the time to get up and get the motion detector going. 0.02 times 0.02. Area is 0.0004 meters squared. L is 0.10 meters. Just want to make sure we get everything in meters here. So we're going to solve for resistivity. All right, little arrow over here. Resistivity is going to be A times R over L. So it's going to be 0.0004 meters squared times the resistance, 16,000 ohms, divided by the length of this object, which is 0.10 meters. We're going to get one of the meters is going to cancel, so we'll get the ohm meters for the units, but let's see if this is something that's going to be on our table or not. So this would be, you know, a bit of forensics work here. Resistivity is 64 ohm meters, way bigger than anything on this table, way more resistive than any of these things. So it's definitely not one of these metals. Well, what the heck is it? I don't know. Some sort of alloy, some sort of, you know, semi-conductive material, some silicon with some impurities in it. Who knows what it is? We could use that as data to try to figure out. So that's it. This is not something, this is mostly for Regents exam. I don't know that we'll actually get to it in advanced physics, but there it is.